right, well, critical to the study of forested ecosystems is really kind of focusing on what lies beneath, essentially, because really we're looking at the vegetation that's occurring in a place, and there's a lot of factors that influence vegetation, including land use history, but much of it is tied up in the ecological potentials of the soils on a site. And so we wanted to take a few minutes here to dig into the soils of at least this spot in Centennial Woods, knowing that they're quite diverse across the landscape, but look here and see what we can learn about a few things about the history of the site. And when I say the history, I'm talking largely about the glacial history and the post-glacial history. And we want to be thinking about the chemistry of the soil, how the soil particles interact with water. For instance, how dry or moist is this soil? And then ultimately, something about its nutrient content, and what do these plants here have to work with? How are they both influencing the chemistry of the soil, and how are they deriving their nutrition from the soil? So I've taken my shovel and I've dug sort of a 1 foot by 1 foot square and pulled out the sod here, which has its own integrity. And actually you can see there's layers in the soils that show as you go down from the surface. And what I'd like to do is have you kind of focus right here on the soil profile. It really is interesting. A lot of people don't pay a lot of attention to what's happening beneath, but when you actually take time to dig in, you can see that there are colors as you go down, and this vertical profile occurs, and that really exposes what soil scientists call the soil horizons. We're going to get to that in just a minute, but before we do that, I want to talk a little bit about what I had to take out of the soil pit to expose the horizons, and that is the soil particles themselves. And boy, just feeling this, it is a very soft, light soil. There are no rocks in here. Unlike down in the stream where we saw a lot of rocks, this is very uniform, very fine particles. In fact, as I feel these, you can figure out the texture of the soil or the particle sizes by feeling them. And largely, this is some very, very fine sands and silts in here. Two questions arise from that, and one of them is, how did these particles get here to begin with? And then also, what happens when rainfall interacts with this soil? Does it kind of get all contained to the surface, or does it percolate quickly down through the soil? In answer to the first question, and we kind of referred to this earlier, where did this come from? Well, these fine silty particles, absence of rocks means that this is really a post-glacial environment in which there was a body of water once covering this area, and fine particles percolated down and collected. And basically, I think it's safe to say geologists have figured out that this is an ancient delta of the Champlain Sea, the saltwater body of water that basically filled the Champlain Valley as the glacier retreated northwards and the waters of glacial Lake Vermont receded, and the salt water of the Atlantic Ocean kind of filled in this area that was compressed by the weight of the glacier. So we basically have water deposited sediments that were an ancient delta, and as you go down deeper and deeper into this area, you get into really silty particles. And so that's what the soil is forming in, fine sands and silts. And as you may know, that if it's really sandy and you basically poured a glass of water, it would percolate down quickly through here. As you get into finer and finer particles like really silts and clays, the water cannot percolate as quickly, and we tend to get more poorly drained soils. But it's safe to say that these soils are they're pretty well drained. And some of that is when we look at the soil horizons, we see lots of kind of rusty colors in here, which means that oxygen has gotten in there and almost rusted the soil and oxidized the iron. So that's a little bit about the texture of the soil and the origin of what we call the parent material of the soil. Let's return now to those horizons, and it's really cool to look at this. This top horizon here, this upper part, is actually the contribution of the forest environment itself to it. It's the needles and leaves and twigs. You know, there could be owl droppings in here, decomposing animals even, but this top section here is really what we call the O horizon, and it's the organic material. And I'm going to take some of this and put it in my muffin tray here to kind of separate it out and we can see these horizons as we go along. And below that, you can see there's this darkish horizon here, and if I pull some out, it's this beautiful dark material. And this is because it's the combination of organic material mixing with mineral material. And this is called the A horizon. And together, these are really the topsoil. So we have the O horizon, which stands for organic. A is just the first letter of the alphabet. But that's that typical zone where organic and inorganic materials combined. What's really interesting on this bed, and you might be able to see it here, is there's a slight little bit of ashen color right below the A horizon. And this often occurs in acidic environments right at the base. And I'm going to put a little bit of that in here, and you can almost see the color difference as you go from the dark to sort of a lighter color. In some environments, this horizon is really well developed, and we call it the E horizon. And it's the horizon of maximum leaching that is occurring as organic acids and water move down through and basically deposit minerals and humus down into the horizons below that. And as we get down into that, we get down into what is called the B horizon. And you can see here the B horizon has a dramatically different color. It's this really rusty color here. And it turns out that as water moves through, and actually, you know what I'm going to do is put this up here in this here. Let me put it up in this well. And you can see that the water would be flowing from here to here to here to here. It's stripping irons and depositing them down here. And then it turns out that as the iron is oxidized, because these soils are pretty well drained, we get this rusty colored B horizon. So we've gone to O to a little bit of an E forming here, into the B horizon. And as we go down further, this may go down for several inches. It often gets lighter as you go down because it has less of the iron that's been deposited. And if I had my auger with me, I might go down even further and get down to really the original parent material of the soil, which is not really interacting with roots and the organic pieces, and we get down to that silt that is really originally deposited in the Champlain Sea. So these are the horizons again, and this is a really a great feature to illustrate here in Centennial Woods. Really important, though, to the plants is to look at the chemistry of the soil. And so what I want to do is, I brought my pH kit with me that has some it's got some reagents here. It's got a chart that basically shows us, can allow us to detect the pH of the soil. And as you probably remember, pH is a measure of essentially the acidity of the soil. And if we get a little more technical than that, it's really the concentration of hydrogen ions in the solution of the soil that we're detecting. And pH is a logarithmic scale. It goes from 0 to 14, at least theoretically, with 7 being neutral in the middle. Most soils go from a pH of about 4, maybe to 8.5 in Vermont, with the average usually around 4.5 or 5. Most are like that. Here in the Champlain Valley, things are a bit different because of all the clays and the proximity to the carbonate rocks that lie beneath. But we're going to do a pH test right here, and we're going to test and see what the pH of the soil is here, because it turns out that by measuring pH, you can infer what the available nutrients are to plants as well. Essential nutrients like calcium, potassium, and magnesium. Really, a low number like 4 means you have a really acidic soil with a high concentration of hydrogen ions, and therefore a lower concentration of other positively charged ions like calcium, potassium, and magnesium. If you have a higher number, like 7 or close to 8, that means that you have a sort of a more neutral soil, lower concentration of hydrogen ions, and more available plant nutrients, like calcium, for instance. And so what we're going to do is we're going to test that right now. So I'm going to take one of my reagents, reagent N, which basically reacts with hydrogen ions. So I've put 2 drops in that well. I'm going to go down about 10 centimeters, and I'm going to add just enough of the soil particles there to soak up that reagent N. Then I'm going to mix it together. And what's happening now is that the reagent is interacting and reacting with the hydrogen ions that are in the soil. Now I'm going to make that, there's a color change occurring. and I'm really making a flat sloping surface there. Then what I'm going to do is take this reagent M. All sounds sort of mysterious. This one doesn't really react, it just really makes the color come out so that we can compare it to our color chart. So I'm putting some on that, on the surface, and then I'm supposed to wait up to 2 minutes to get the full change. But you can already see here that now I'm getting a color change, and if I align it there, I can figure out, well, what color is that turning? And actually, this is fairly acidic soil here. It's not turning blue, it's actually staying sort of yellowish green. And I would say, just looking at this, is that we have a pH of about 4.5 here, which is on the acidic side of things. And when you think about that, what would contribute to that? Well, the fact that we have all these pine needles and cones and really all this acidic material that's leaching down into the soils really influences the pH. And the fact that we don't have rocks here with calcium carbonate, we have all this kind of sands and silts, these don't do a whole lot to buffer the acidity. And so we're getting fairly acid soils. And that is very much reflected in the vegetation around this site. Pine trees, white pine can grow very well in acidic, well-drained soils. Hemlock, which also is very common in the site, does particularly well in acidic soils too. And we're missing a lot in here the species that are rich site indicators. So when we look at the forest here, it's largely a reflection of what lies beneath. Life is impacting the soil, but it's also being affected by it.